Here's another exponential growth and decay example. This one is decay. The last one we looked at was growth. Iodine-131 is a commonly used radioactive isotope that helps detect how well the thyroid is functioning. Iodine-131 decays exponentially, and after approximately 8 days, only 1/2 of the original amount remains. If 5 grams of iodine-131 is present initially, find a function that gives the amount of iodine-131 in grams t days later. Okay, so we're looking at t in days. We're looking at amounts in grams. We're looking at 5 grams initially. We're looking at 8 days. Half is left. That's called its half-life. Okay, so again, just like in our last example, all we're doing here is finding a formula. So all we need to do is find K. And we don't actually need to use that formula to solve anything yet. All right, so we have our formula. Formula for our function is A equals, I jumped the gun putting my sub-zero. A equals A sub 0 e to the kt. Okay, so we know that we have 5 grams present initially. And we know that in 8 days, we end up, so t is 8, and then this is k. So t is 8, and I just swapped them so that my numbers first. So k times 8, or 8k, we're going to have half of the original amount remaining, so that would be 2.5 grams. Okay, so there we're all set up to find k. So our first step, just like we've been doing in every problem, is to get rid of that coefficient. That leaves us with 1/2, or you could call it 0.5. And that is known as the half-life of a radioactive isotope. It's called radioactive decay. That equals e to the 8k. So now we're going to do the natural log of 0.5 equals the natural log of e to the 8k. And we can move the 8k to the front as a coefficient. And we have the natural log of 1/2. So then we can, oh yeah, natural log e cancels out because it turns into 1. So our k value is just going to be natural log of 1/2 divided by 8. That's our exact answer that we could use in our problems. Or we could find an approximate answer, which is negative 0.0866, and use that in our function. So there's 2 different ways we could write out our function. We could write it as 5e to the negative 0.0866 k t, because that was k, so we're putting that in for k. Or if we want a formula where it's actually going to give us exact instead of approximate, we can just leave our original answer, the natural log of 0.5 divided by 8. There's our whole k value times t. So then just using that formula and plugging in whatever t value will give us a more accurate version of the answer if we were going to use this formula.